So now we've reached the step 5, and you have the training the data set and predicting it, right? And if you think about it, while training you might do it in batches, but when you predict it, right, you don't need to create a batch of 120 sequences. You just need a batch of one sequence, right? Because you are only trying to predict an output for only one sequence at a time, and you don't predict now for 120 sequences at the same time. So you pass in one sequence as input and create a output or predict for only one sequence. So when you predict it, you should probably change the batch size to 1, because you are only basically doing a prediction for only one sequence, right? So that's the story here. So that's something that you will come to see in step 6, but I just wanted to give you a heads up there. So we are going into the training the dataset here. So we jumped into training the dataset. So the first thing we should know here is we have 3 layers here, right? So obviously your LSTM is going to do the RNN, recurrent neural network training. So that has to be there, and your output layer has to be a dense layer, which is connected to all the internal neurons, and your output size of your output layer has to be the size of the vocab size. So why does it have to be the same as the size of the vocab size? So the reason is simple. The reason is that let's assume that you have 79 different types of characters in the data set, or it could be like only 26 if you are only using alphabets, removing everything else. There is 79 or different possibilities that the next character could be. It could be one of the alphabets, or it could be one of the special characters or numbers that you had in the original data set. There is 79 different possibilities that could be the next character, and each character, the possibility, has a corresponding probability assigned to it, right? And your output will have, the model will give a probability for each of the characters, and you can pick the best probability, or you can pick the surprising options depending on what type of prediction you are trying to do. But it basically helps you predict it that way, right? So the first step is here to create a model, right? And I'm using sequential to add layers to it. Sequential is a Keras library which helps us to add layers to it. So we have 3 layers. So the first layer is your embedding layer. So embedding layer is used to represent your input data that in n number of dimensions. So in this case, we picked 256 as the embedding dimension. So it represents the data in 256 dimensions, and so that's basically your input layer, and then your neural network layer. So this is the critical layer here. So if you see the number of neurons in that is defined as 512. So since it's assigned as 512, you will have 512 neurons here in this layer, and then you have initializer as glow rod uniform, and this is something that you can try around different options here, but you can just go with default this for now, unless you understand what each of these things are. So you create a model. That's the first step, and you can see the summary of the model. So if you see here, it says you have 3 layers. This is the first layer, and the second layer is an LSTM layer, and the third layer is a dense layer, right? And if you see each element, thing has this many number of neurons, right? So the embedding layer has 256, LSTM has 512, and your dense layer has 73. So I guess we had 73, but the vocabulary size was 73, right? So 73 different possibilities that you can have in the output. So that is how you go into this mode. And now, now let's take us, even before we train, let's use this model to predict something and see how the predicted output looks like, right? So basically what they're doing here is they're taking an one element from the dataset. So dataset will have your input sequence and also the output sequences, right? So in our case, you'll have 120 input sequences in a particular batch and 120 output sequences. So this input example batch will have 120 input sequences and target example batch have 120 output sequences. So this model of this call basically is calling, now passing this input 120 input sequences to the model and creating 120 example predictions, 120 sequence predictions here, right? And they are printing this as now as an output. So if you see here, so the prediction basically has 120 sequences. Each sequence has 130 characters, and each sequence, each sequence prediction has 73 different possibilities. So that's how it's structured. So it's actually a three-dimensional array, I guess. So it's hard to visualize, but this is the gist of it. So each sequence has 73 possibilities. So that's how it's actually defined here, right? And this is just to see how the predicted output will look like even before, just a shape of it, even before we go into prediction. So this is, and they have even sampled it, sampled a prediction here. So they've taken an example batch prediction out of the 120 sequences. They're taking one sequence here, like now they've taken one sequence, and out from that one sequence, right, the one sequence might have 73 different possibilities. So they are taking one sample out of it, and then take that as one. That's one, right? And this helps to reduce the dimensions. This squeeze of function reduce the dimensions. So it's a three-dimensional right now. So this will help you reduce one of the dimensions now, since you have picked only one possible outcome here, right? And there is no need to have that many number of dimensions here. So they've reduced it, and so this is one of the predicted target sequence for one of the input sequence, right? So you could just pass it to that into vocab array and get the corresponding text also, but basically it's just predicted some bunch of things based on even before it's actually trained, right? So these are little things, but it helps us visualize how the data looks. Okay, let's just jump into training, right? So let's go into training. So you've reached the last step in the training section. So just before you train, there is one step that you need to do. That is, you assign or compile with an optimizer and provide a loss function. So this is applicable for every single machine learning algorithm, right? So there has to be an optimizer that actually provides reduces the provides the best parameters. We could see best parameters in the sense it optimizes all the neuron values so that it produces the best output when input is given, right? So there is gradient descent is probably the simplest of them all, which helps, but Adam optimizer is actually is faster comparatively, and there is stochastic gradient descent, which is actually more accurate but less faster. There are a couple of things, a couple of other optimizers also that we could use. So gradient descent is easier to understand. So most of the examples you see gradient descent used as an example, but Adam optimizer is faster, so we'll probably use that here. And we have categorical cross entropy as your loss function. So why do we use sparse categorical cross entropy as your loss function? Okay, so there are since this is a classification algorithm, right? Basically, you are trying to find out which is the best among a given list of options. So which is the best next prediction or next character out of that 73 characters. So you are basically doing a classification model, and then since this is not a binary classification, right? You are not saying whether this or that. So it's 73 different possibilities. So if you're probably doing a binary, you'll probably classification, you'll probably use binary, class, categorical cross entropy. I think so, but here it's 73 different out possibilities. So that's why we go for sparse categorical cross entropy. And there is something that we need to remember here. By default, this is false. Okay, so I've taken that sparse categorical cross entropy and change that to true. Okay, so when you say from logits, right, is equal to true, by default it's false, right? So since by default it's false, what it would assume is your target is basically a probability distribution. So I don't know why by default it's considered done that way, but it has to be logits, so that since you are giving different options, not a probability distribution of the different options. Now to train it, we are directly giving the values itself, and it has to figure out what is the best one among that. We are not actually already telling that what is the probability of that particular event happening, right? So it has to be from logits equal to true, to make sure that it works without any issues. I originally did not notice this. I was doing some trainings and I noticed that the loss is actually never going down. So we could actually try that also. So let's run this one. Okay, 300 epochs is probably required, but let's do it for 100 epochs. So if you see the loss here, it's actually not reducing at all every iteration or iteration. So I've directly used sparse categorical cross entropy as your loss function, but unfortunately it's not going down at all. From here you'll probably able to see it's just going up. In some cases it's 2.6, then 2.8, 2.7, again 2.6, again 2.6, then again 2.7, 2.6. So this is not what we expected. Okay, I'm back after a short break. So our model is already trained. So as you can see, it has trained 100 iterations and it is completed the training. So what I'm going to do is from the history of the loss and also accuracy, I'm just gonna load that history to a data frame and then use the plot of that inbuilt function in pandas to plot it basically. So it's going to plot using the matplotlib inline function. So if you're providing this matplotlib inline function, basically how it helps is it will show the plot in the Jupyter notebook itself. So this is the plot that we have. So the blue line is the loss function and also the orange line is the accuracy. So you can see that loss is decreasing really well. It has started above 3 and now it has come to almost 0.8. So you can still keep going, couple of more iterations, it will help to improve this process, but right now, so what we have is reasonable enough for us to go for a prediction. And similarly, accuracy, as you can see, is also increasing gradually, which is a good sign always that it's actually working as expected. So that's we come to the end of the step 5, which is the training. So far we have covered 5 steps. That's pre-process, where we go ahead and clean up the data in whatever format we want. Step 2 is where we encode the data. So convert sequence of characters to a sequence of numbers, and also create an array to do the reverse encoding also. And then we go ahead and do the creation of sequences. We use the Tensorflow slices, which is a Tensorflow inbuilt library to create sequences. So we split the entire data set into sequences of same length, and if there is a sequence that could not be fit into that length, we dropped it. Probably one sequence which is not complete at the end probably will get dropped, depending on how many sequences we selected, right? And then we went on to do the batch creation again. Then we picked a group of sequences as one batch, and created multiple batches. Before that, we also create, once we created sequences, we also mapped it to its target, to ensure that we have a source and also target to train on, right? The corresponding target for the source. So those are the steps that we did. And step 5 is where we did the training. So we created a model, and then we added the loss and the optimizer and the loss function. And the most important thing is, since we are adding sparse categorical cross entropy, so if you can see here, I've added overridden the default value. So if you see the default value here, it's actually from logits equal to false. So I have overridden that to true, so that it works as expected, right? So if it is from logits equal to false, then it would assume that your target parameter is actually a probability distribution, so which is not in this case. So it has to be this parameter has to be true, so to get a good accuracy and loss, right? So we see that it has done really well.